Today we're talking about limits and continuity and whether functions are differentiable at certain points. So before we start to go over this, I need you to read pages 420, page 421, over to the middle of page 422. And when you finish reading that, you can go ahead and turn the video back on. I'd go ahead and stop it right now and read those pages. Okay, on page 420, you see the definition that we used for derivative last semester. The first derivative evaluated at c is the limit as x approaches c of f of x minus f of c over x minus c. And if you look at the pictures on page 420, you'll see that the secant line that goes through those curves, that's the slope of this right here. It's the slope of the secant line. And what happens is we let x and c get closer and closer together so that this difference right here approaches 0. So the points are almost on top of each other that we use for the slope of that line. So on page 421, it says if the derivative exists at c, then the limit as x approaches c of f of x is equal to f of c. In other words, on that graph that they gave us, one of them like this, where you have the 2 points, if the 2 points just get closer and closer together, then they become the same point, so that the y values on both of them would be exactly the same. All right. So then over on page 422, they have a really nice graph of a curve that has 2 cusps or 3 cusps. That's a sharp curve where a sharp changing point where the curve comes to a point. You can see it on page 422. And also they have a vertical tangent drawn. Wherever the vertical tangent is and at any of the cusps, the derivative is not defined. So what we're going to do in today's lesson is we're going to use left-hand and right-hand limits to prove that derivatives don't exist or do exist at points. Because if it's true that they do exist, then the derivative has to be the same on both sides of the point that we're talking about. So if you look at 82.1, use left and right-hand limits or derivatives to determine if f of x equals the absolute value of x minus 2 is differentiable at x equals 2. Well, the absolute value of x minus 2, what we need to do in order to look at the derivatives, which is what it tells us to do, is we have to define this. F of x, if this is a positive value, would be x minus 2. And if it's a negative value, then it would be minus x minus 2, which would be the same as negative x plus 2. So we have to consider both of these. And if you look on page 422, they graphed that. So it's this v, and we already knew it was going to be over 2 units right here, like this. We knew that that was the shape of it. And based on what I told you just a minute ago, anytime we have a sharp point in a curve, the derivative is not going to be defined at that sharp point. So we already know that it's not going to be defined. But what we're going to do is use derivatives in each one of these equations and prove that it doesn't exist. So we're going to take the derivative of the first part of this. So the derivative of this is 1. And then the derivative, I'll call it g, of this one is negative 1. All right, so that proves it right there. On the left-hand side, it's x minus 2. On the left-hand side, it's negative 1. And on the right-hand side, it's positive 1. So because the derivatives are not equal, then this curve is not differentiable at x equals 2. All right, so we used derivatives and we determined that on one side it was a positive 1, on the other side it was a negative 1, which tells us that it's not differentiable at that point. That is the critical point for this graph, the only critical point. So it's not differentiable at that critical point. All right, let's move on to the next one. It says, for what values of x is the piecewise function shown below differentiable? So it's f of x equals x squared when x is greater than or equal to 1. And it's 2x minus 1 when x is less than 1. All right, so let's graph that piecewise function. So we know that this right here is just a regular parabola. Its vertex would be at 0, 0, but because we're talking about x greater than or equal to 1, we plug in 1 here. So 1 squared would be 1, so it's here. Over 2 squared would be 1, 2, 3, 4, so it's the parabola that does this. And then when it's less than 1, it's this line right here, which was 2x minus 1. So its y-intercept is negative 1. It has a positive 2 slope, so it goes right here. All right, so right here at this point, these two graphs come together. Because at 1, this would be 1 for this equation, and at 1, it's 1 for this equation. So it's asking us where this function is differentiable. Well, is there a cusp here? Is there any point where this is not continuous? No. So that means that it's differentiable for all reals. Okay, it's continuous, no problem. All right, one last example on page 423. It says, let f be defined as f of x is equal to absolute value of x plus 3 when x is less than 1, and ax squared plus bx when x is greater than or equal to 1. Ax squared plus bx is the graph of what? It doesn't really matter what a and b are. What is the shape of that curve going to be? It's going to be a parabola because of the x squared. This is an absolute value graph. Remember, absolute value of x by itself would just be this guy right here. But with the plus 3, it means it's shifted up 3 units. So if we graph this, 1, 2, 3, it goes like this. And it's less than 1, so I need to erase here. Less than 1 means I need to put an open dot here. And this thing will go up like this. So there's this part of it. Now this is the one, what we want to do is find out what A and B have to be in order for this graph to be continuous. So it's going to have to be the same y value for this graph as this one would have been. So that y value is 1, 2, 3, 4. So I know that ax squared plus bx has to be equal to 4. I know that because I need the y values to be the same. And that's at x equals 1, so I can plug in 1 for x. So a times 1 squared plus b times 1 is 4, which gives us a plus b is equal to 4. So we know that. A plus b has to be equal to 4. Now, in order for this to be differentiable, remember, the derivative on this side has to be equal to the derivative over here. So we know that on this side, the equation of this line right here is just x plus 3. So this would be f of x is x plus 3. So then f prime of x is going to be positive 1. Which means in order for this to be continuous, the derivative on this side also has to be positive 1. So let's take the derivative of this function. So g prime of x will be equal to 2ax plus b. And we know that in order for it to be continuous, the derivatives have to be the same. And since this one over here is 1, we can set this equal to 1. And we also know the the x value is 1 because its x is greater than or equal to 1. So let's plug in a 1 for x. So that gives me 1 equals 2a plus b. So I have this equation and I have this equation. Now we can use substitution and elimination to solve for this. So if I multiply this by a negative 1, that becomes minus a minus b equals negative 4. And if I bring this guy right here, that's 2a plus b is equal to 1. So that's a is equal to negative 3. I can take that negative 3 and put it right here and solve for b. So 1 equals 2 times negative 3 plus b. 1 equals negative 6 plus b. So then b would be equal to 7. So a is negative 3 and b is 7. So then that equation would become y equals negative 3x squared plus 7x. So if we look back at this curve, this happens to be a parabola that opens up like that. Okay, and with the a and the b that we found, we know that that would be a closed dot. And that's what we wanted. We wanted it to be continuous so that there's no sharp corner right here at x equals 1. So in order for it to be continuous, a needs to be negative 3 and b needs to be 7. All right, so this is going to be due on Wednesday. Make sure that you write at the top of your paper how many problems you completed. And then you can scan it in with Scan Genius, or you can take a picture of it and upload it into Canvas. All right, thanks and have a nice evening.